So let's talk a little bit about data. No, so data is not made in heaven. Data is usually acquired by someone to answer a very specific question. And we want to ask our own questions with data that exists, or maybe data that we get ourselves. And we want to do two things. Now, we want to be agile with data. We want to use the data to really ask the questions we want to ask. And when we try to answer questions, we want to make sure that we don't lie to ourselves. Now, it's difficult to overestimate the need to think about your questions. So it's not that deep learning is like the best machine learning technique. Not like deep learning is a technique that we use to ask a very specific kinds of questions under a specific set of circumstances. And we want to be very clear about that. The first thing that I want to really make sure we all understand is let's not lie about data. In deep learning, we generally do predictions. Now we have some data set, we have some items, we have some data about them, we want to predict something. The label, we want to predict what number is that, we want to predict does that person has cancer. When people speak with us as data scientists, they often want answers to causal questions. They don't want to ask, do people who take aspirin die earlier? They want to ask, should I take an aspirin and will that allow me to, on average, live longer? So many times, machine learning and deep learning researchers are being asked causal questions by the world, and the prediction that we do doesn't really speak to that question. The real world differs from our data set. The data sets that we have are all biased in lots of ways. And if we take the data set from one place where it was taken to answer the specific questions that we're into, our performance might be quite bad there. It's a concept called external validity. And one of the easy things to do is to use validation to avoid us from lying about data. So what that means is if we train on the same data set that we test on, we will have massive overfitting. So what we want to do is we want to split the data into a data set on which we train that is only used for training and another data set that is only used for testing. Under a lot of circumstances, you want to have another data set that you don't even look at. But let's stay away from that. But for hyperparameter optimization, you need to further divide the training set. You will hear more about that at a later point of time. So you need always the data on something you train on and on something that you test on. Moreover, this division between validation and training data set, you want to be very careful, because if there's things that are shared between them, it will make you look very good, even if you shouldn't be. So here's an extreme case of this problem, something that often happens in machine learning. Let's talk about, let's say we want to do a medical prediction. Maybe we want to find out if people have Parkinson's disease, if people have some kind of a disease. Now, how does the real world look like? We will get data from a bunch of patients, and for those patients, we will know do they have the disease or not. And then we have a new patient who comes in, we don't yet know about them, and we want to say, you should be checked out. This is looking a little like you might have that disease. Now, in this case, how does the world look like? We get data in subject by subject, and we will have to predict a new subject from it. Now, there are some people who use what's called record-wise cross-validation. It turns out that it's very expensive to get data from lots of people. So what they do is they take maybe 20 subjects, they get 10 recordings from each of them, and then they take all the recordings but one to predict what they have in the other parts of the data. So what that means is they try and predict. They have, let's say, from Conrad, they have 10 recordings. We know that Conrad is healthy as far as we know, and so what they do is they then take some samples in the training set, which contains Conrad being healthy, and some data sets, some parts of the data set where they say, can you now predict Conrad on that recording? But of course, this is not like it is in reality. And it makes it that you can be good at disease recognition if you're good at subject identification. Now, subject identification is usually very easy. So you want to be very careful about that. So it turns out if you do what's called record-wise cross-validation, about half of the field does that mistake, and it gives you massively overinflated confidences. It looks like your machine learning system is wonderful, even if it does absolutely nothing useful. I should also say there's generally overfitting. Don't trust yourself. Overfitting is massive if you have smaller data sets. So if you have any shared information between the training and the test set, you will be doing too good in your validation. And ideally, you want to have part of the data set you don't have access to. And I want to mention that this is even a problem for huge data sets. So Ragt et al. Re-obtained data just like ImageNet, and what they found is that the existing algorithms are considerably worse on these data sets. So you always want to have a clean division between training and test data set. Here's how to do it. You load the training samples and the code already gives you the data to do that. Not like you say train is true. This is the training part of the data set. You have the training data, and then you have the test data, and then you will use this part here, the training samples, for training, and the others only for testing. You will never use it for training. So let us load some data and divide it into a train and testing data set, and see how CIFAR train and test data set are loaded.